This is about PyMC. There are some alternatives to PyMC. I don't know really anything about them other than the names. Stan, Being Machine, Edward. I'm not going to talk about them. There's quite a few advanced techniques. As you'd expect, PyMC has a forum where people ask questions and various experts contribute. There's a lot of discussion of advanced techniques. I'm not going to talk about any of those advanced techniques. This is going to be about the basics. Finally, there are the algorithms that make the engine work are really interesting, actually. And in particularly Hamilton Monte Carlo is a very interesting algorithm. But I'm not going to talk about it. I'm going to instead give you some very simple intuition about how it works. The simple intuition is not true, but it's a working mental model, and you know it's true enough that you can understand what's going on. So let's talk about our journey tonight. We're going to start with a very simple model and a very low fidelity model. We're going to enhance it, make it a somewhat more complex model, somewhat higher fidelity. Enhance it again, more complex, higher fidelity, and further and further and further. So we're going to, it's a succession of models tonight, all in PyMC. And now let's talk about the origin of tonight's data set. So at the beginning of the pandemic, intersection number 2, the beginning of the pandemic, like all of you, I was a little bored with the lockdown. And at that time, I'd been fooling around on the trumpet for a few years, but fooling around is the operative verb there. I hadn't been very disciplined about playing. So at the beginning of the pandemic, I hired a trumpet teacher who had intended to be here tonight, by the way, driving out to Baltimore. Hired a trumpet teacher over Zoom, and got disciplined about it, started practicing an hour a day, which is what you really need to do. How many people have played a musical instrument before, by the way? Okay, so you know. You need to practice a fair amount and every day to make it work. This, by the way, is the great Polish trumpeter Tomasz Stanko. So the origin of tonight's data set is really has to do with that work, that daily practice. So my daily practice routine is I do some more, not atypical, by the way. I do some warm up, 10 minutes of warm up or so. Then I do technical studies. I play technical studies. I'll talk in a bit what technical studies are. Then I play riffs. These are memorized musical phrases that I want to drop into some improvisation in the future, so I want to be able to play them at a moment's notice. And then I play songs, and various, mostly jazz standards. So let's talk about technical studies. What are technical studies? These are playing from sheet music, and they're designed to improve your technique. So you play these technical studies and get better at them, and you can improve your general technique. And I have technical studies from like 4 books, and then some more that my trumpet teacher has contributed. This is an example of one of them. This is from this book, written, first published in 1908. I think my copy's from like 1909 or something. It's very old. So how many people can read music? How many people cannot read music? Okay, come on. I'm going to play this technical study for you. I'm hoping this goes well. You never played a technical study in public. I do play in public nowadays, but I've never played a technical study. So we'll see how this goes. Where's my little one?
That sounded great.
Now I play that part again. Then I play that part again. Ben suggested I do that, by the way, so I thought if it didn't go well, I would blame him. So yeah, so that's an example of a technical study. So there's a lot of them. What I've been doing is tracking the number of mistakes that I make on different technical studies. So what you see here is a grid, a spreadsheet of how many mistakes I've made each day on which technical study. So the circled one there is I played technical study 140 on February 15th. For some reason I didn't practice on February 14th of this year, I'm not sure why. But February 15th, and I made one mistake. I made one mistake on technical study 14. So there's 227 technical exercises altogether. I don't play them all every day. That would be impossible. That's just too many. So I play like 8 to 12 every day, and I use a spaced repetition application to tell me which ones to play on which day. So this is the data set. This is the data set we're going to look at with all the models tonight. This is the whole data set right here in a graph, in a plot. The practice days along the bottom, you see the horizontal axis is the practice days. The vertical axis is the mistake count of an exercise on that practice day. So it goes from 0 to, I think in some cases, 11 mistakes on a technical study. You might notice that the days don't start at 0, they start at 300 some odd. And that's because I had been recording since August of 2020, August of pandemic year, which technical study I was playing which day. But it didn't occur to me until about a year later that I could count the mistakes as and record the mistakes. So I only have 2 years and a few months of data for the number of mistakes that I've made. So, am I getting better? Maybe. Maybe, I don't know. There seem to be more zeros, but on the other hand, I've added some exercises in here, so I don't know. So let's. The other thing about that whole data set, by the way, is that a lot of the technical studies are incomparable. You know, there's different kinds of studies, and you know, making 3 mistakes on one study is as good as making 0 mistakes on another study. So it's a little hard to tell. So let's restrict the data set now to just the 7th Clark study. In the Clark book, the 7th study, and I just played one of the 7 studies. So now we've got 15 exercises altogether. It's the same music. If I played all 15, and I'm not going to, but if I played all 15, you'd say, yeah, they sound the same, they're just higher or lower, and they're in different keys and stuff. So these are all comparable. These are all the same piece of music. So the 7th Clark study data set looks like this. So again, we've got a dot here for the number of mistakes, the mistake count I made on a particular study on a particular day. So maybe I'm getting better. I don't know. I'm not making so many 11s anymore or 8s.
Real quick question. I don't think you're making 1.2 or 2.9 mistakes on any given day.
I've jittered.
Noise just that we can see it.
I've jittered it. Yes, thank you. Thank you. I've jittered it so you can see it. Added a little noise to both the days and the mistake counts, so it's easier to see. So let's fit this to a model. And so first we got a data wrangle. I'm not going through the details of the data wrangling, but the outcome is like this. We have a row for every exercise of the 7th study played at some time over this two-plus year period. For instance, back on day 364 of my record, I played exercise 135 and made 6 mistakes. Whoops, that's a lot of mistakes. Same day, I played exercise 142 and made 6 mistakes. Next day, I played exercise 139 and made 2 mistakes, and so on. You might be wondering, by the way, how do I count the mistakes? I hear them. I hear them and they pain me. That's how I count the mistakes. So what is a mistake? Different ways to make a mistake, but the main way is to play the wrong note. So I've circled an E here, and if I instead play an F or an E flat, that's the wrong note. If I play an A, that's the wrong note. And on a brass instrument, there's 2 ways of playing the wrong note. So the E has the first and second valve down like this, So one way of playing the wrong note is to have, the wrong valve combination. But on a brass instrument, there are many notes that can be played with the same fingerings. So for instance, that's the E, that's an A, another A, an octave up, C sharp, another E. I can tell I haven't warmed up here. Maybe I won't go any higher. And that's all called embouchure. So it's a combination of muscles, teeth, tongue, breath. Collectively, it's called embouchure. And so with different embouchure, you can play different notes with the same finger. So let's go to the first model. So the first model, kind of a null hypothesis, is I'm not making any improvement here. It's the 3+ years, same skill. So let's walk through this model. First of all, third intersection with the pandemic. At the beginning of the pandemic, realized there weren't going to be any data science DCs for a while, and so Peter and I stood up a study group around this textbook, Statistical Rethinking. Very excellent textbook, but it is a textbook. It takes some real effort to read it. And so Ben joined, Jay joined, Aaron joined. Where's Aaron? Aaron joined, and then later Nate joined and JK joined.
Very cool.
And so we read 2 chapters every month. We talked about it over Zoom. So I'm using the notation from this book in order for the statistical notation of the statistical model. So mistakes A is the mistake count for one exercise attempt. So I play exercise 138, I make 2 mistakes, that's a count of 2. This is a binomial distribution. The mistake A is a draw for binomial distribution, which just means that we're combining a bunch of individual chances of making a mistake into a count. So I play the whole exercise. There's a lot of opportunities for making a mistake, one for every note. We combine them all, we get a draw into a count of mistakes. There's a chance of mistake for each note. There's 199 notes in the Clark 7th study. I didn't play a whole 199, I skipped the repeats. But if I played them all, there was 199 notes. So that's one line of the statistical model. And the second line defines the chance of making a mistake on any individual note, mistake sub p. And so for a Bayesian model, we have what's called a prior distribution, which is the distribution before you see any data. Often a guess, sometimes informed by science, sometimes informed by kind of your understanding of what's going on. So we're going to say this is a triangular distribution, guessing this triangular distribution. I know I'm not making 0% mistakes, because I know I'm making some mistakes. I know I'm not making 10% mistakes, because I've never had more than 11 mistakes on any. So somewhere in that range. And it's a wide range. This is called a weakly informative prior. So we're going to give it this prior. Now, how do we express this model in PyMC? Very much like the statistical model here. Well, we've got this expression here for creating a new model, for pm.model and then parentheses, and you use that model for the context of all the individual variables that follow. We're going to assign this to model 0. So why are we assigning it to variable? Because we're going to use it later to do various things, basically. So we're assigning it to a variable, and then we create a triangular distribution. It's basically the same. It's just different syntax on the same as the statistical notation. And then we have a binomial distribution for the draw of the number of mistakes from the 199 chances of making a mistake, and that's then fit to the observed mistakes. So this is kind of the relationship of PyMC to the statistical model. So let's go over to Jupyter and we'll run this. So I've already done all the data wrangling here. So we're going to define the model. We're going to sample from the model, and I'll talk about what sampling means in a second. It happens very quickly, and for this simple model, it happens very quickly. And then we're going to look at the posterior distribution. So posterior distribution means what's the probability distribution of this variable after we've seen the data, after we fit to the data. A little bit further down. So first of all, first thing, this is mistakes P. So this is the probability for any individual note of making a mistake. And you'll notice there's not much uncertainty here. Everything here is between, most of the mass is between what 1.04% and 1.14%. That's not much uncertainty at all. The PyMC is very certain that this is right about 1.1%. So what? Go ahead.
Sorry, I don't see T as a variable there. So you were talking about whether you improved over time. So
Not yet.
Okay,
not yet. This is the null hypothesis that I haven't improved over time.
Oh, right, all right. Okay.
So,
okay,
thank you. So how do you interpret the posterior distribution? What it means is, if the model is correct, this is the probability distribution of mistakes P. Now the key thing there is if the model is correct. If the model is correct, we know very precisely that the probability, the chance of making a mistake is roughly about 1.1%. Okay, that doesn't tell us a whole lot. What do we do with the sampling? What was going on with the sampling? Okay, here's where I get into the mental intuition about the sampling. That's not true, but it is a useful mental model. So we have PyMC with the data so what PyMC does in this fictional mental model is it takes random samples from the prior distribution. In this case, there's only a single random variable, and looks at the data and says, how unlikely is this data given this value for mistakes P. So 6.7%, really extremely unlikely. If mistake P was 6.7%, there'd be examples of making 20, 25, 30, 35 mistakes on a single exercise. There's not. So it's extremely unlikely. What about 3.9%? Still extremely unlikely. 1.8%, very unlikely. Not quite as unlikely, but still unlikely. 4.1%, extremely unlikely. 0.8%, getting there. Still unlikely, but getting there. So taking all of these random samples of the prior distribution and then figuring out how likely the data, the observed data, is given those samples and the model. And so you end up with a posterior distribution. Here's the most likely values for mistakes, for mistake underscore P, the most likely values. Now this is only a useful mental model. You could actually do it if you had one random variable like this model. You could actually do it this way. It would take a while, but these computers are fast. It would probably work. If you have 20 random variables, it's a huge space to explore. You'd never get there. The universe would die heat death before you get to the end. So this is not really how it works, but it's a mental model that's surprisingly effective for understanding how this works. Okay, so let's go to another model, one with T in it, one with improving over time. So this is the first line is pretty much the same, except now we've got mistakes underscore P is actually different probability of mistake for each attempt, no longer the same probability of mistake. And that mistakes underscore P is now the initial probability of mistakes at day 0, at the very beginning of the practice back in August 2020, and then a constant linear reduction every day. Reduction in the probability of mistake each practice day. And then day sub A is the practice day that an attempt is made. And then we have two random variables now. We have the initial mistakes P, so this is the probability, the initial probability of making a mistake back in August of 2020. And so we're gonna say, okay, this is, the prior for this is maybe 2% plus or minus 1%, normal distribution. And then the reduction per day, well, it's gotta be much smaller because, you know, every day I'm not improving by 1 percentage point or 1/10 of a percentage point or even 1/100th of a percentage point. So maybe it's a normal distribution with a very small standard deviation, and let's call the mean of the normal 0 because maybe I'm getting worse. So two random variables. Normal distribution centered on 2%, normal distribution centered on 0. Oh, and then we express it in PyMC. So initial mistakes P is now a random variable with normal. Not surprisingly, normal is a primitive in PyMC. So we give it the mean and the standard deviation. Similarly, reduction per day is a normal with a mean of 0 and a standard deviation of 0.0002. Now we got a new thing, deterministic. So what is a deterministic? A deterministic is a variable that is completely determined by its components. So it's not a draw. It could incorporate some draws. It could incorporate some statistical draws, but in itself it's not a draw. It's complete. If you knew the reduction per day and you knew what day the practice was on, you'd know the reduction in daily practice since the beginning, the reduction in probability of mistake in daily practice since the beginning of since August 2020. And so we have another deterministic that is now defining mistakes sub P, the probability of mistake, which is the initial probability of mistakes minus the reduction due to daily practice. So we're getting better and better every day. We start with maybe 2% mistakes, we get better and better every day, and we end up somewhere better. And then mistakes is it's the same actually as in the previous model. So let's switch over to Jupyter again. Anybody got a guess about what's going to happen?
Learning. Gentle slope. It's gonna take longer.
Takes a little longer, you're right on that. And we get an error.
No.
We get an error.
That sounds right.
Does it go negative or something?
You're on top of it, yes.
Oh.
So, so this is something else I learned with my study group partners in the McElrath book. This is Andrew Gilman's folk theorem of statistical computing. When you have a computational problem, often there's a problem with your model. 90-some-odd% of the time, that's true. It's very often. So what's the problem with this model? This, by the way, comes from Andrew Gilman, who's a statistical programming expert at Columbia. Professor, writes a blog that's very good. What's wrong with this model? You got it. It goes negative.
Yeah.
It goes negative. It goes negative in two different ways. It goes negative because maybe the initial mistakes, P, the initial mistakes in August 2020, well, this is a normal distribution, 2% with 1 percentage point standard deviation. You know, some of those draws are going to be negative, right? You can't do anything with a negative number to get a binomial count. What does that mean? You know, get a binomial count of 3 with a negative percentage, negative probability? No, it doesn't work. And then also the reduction per day maybe goes negative. So anyway, folk theorem of statistical computing. There's a fidelity problem with this model too, and it's a little more subtle, but I think Sam understands. So to go from 2% mistakes to 1.5% mistake, that takes some practice. It's difficult. It's doable. Go from 1.5% mistake to 1%, more difficult. Even though there's the same linear improvement, it's more difficult. Go from 1% to 0.5%, even more difficult. Getting to 0, yeah. I mean, if you go to the symphony, sometimes I like going to the symphony. If you go to the symphony, occasionally you will hear a brass player miss a note. Usually it's a French horn. Sad but true. And they'll immediately correct it, by the way. It's just a passing thing. I mean, they're professionals, they know what they're doing. If you listen to jazz, go see a jazz performance, you will never hear that, because Miles Davis plans on hitting an F, hits a D instead, he goes with it. He makes it work. So a little difference in genre. Something to be said for that, by the way, making it work, making a mistake and making it work. So, given these problems, what would Jimmy do?
Jump out of a plane.
Yeah, I stole this conceit from Ben, by the way, Ben Clemens. So, I claim if Jimmy was still with us, he would use a log odds scale. He would not have the model expressed as probability. He would have it expressed as log odds. So what's a log odds? It's taking the probability, converting it into an odds. So 0.5 probability 50%, converting it into an odds, 1 to 1, even bet 1 to 1. That's the odds. And then the log of 1 is 0. So we can do this to 0.2. 0.2 probability, that's odds of 0.25, 1 to 4. Log odds is minus 0.602. So the nice thing about a log odds scale is that you can get as high or as low as you want, and they're still mapped into 0 to 1, but still mapped into proper probabilities. So let's do the same model, but now on a log odds scale. So the first line is the same. We still need proper probabilities for binomial draws, binomial distribution. Second line is different. Everything else in the model is going to be expressed in a log odds scale, and then we're going to convert those log odds into a probability. So basically, let me go back up here. Basically, using this curve, visually you can see this on the curve. And the nice thing about this curve is you get better and better and better, but you never quite get to 0. So never quite get to 0 mistakes. And then the priors here, the initial mistakes, maybe minus 4 as a mean, plus or minus 2 standard deviation. We can plot that either in log odds, it looks like just a normal distribution, or plot it in probability. And now you see the log scale on the bottom. And it's not even quite a log normal distribution because of the odds thing. It works out. And then again, we're going to make no assumption of improvement. 0 as a mean for reduction per day, but we're going to express it all in log odds. 0.1 is very optimistic improvement. I'm not getting anywhere near that kind of improvement, but it's a weakly informative prior. Same model now in PyMC, and it's really the same as what you saw in Model 1, except for this. Well, the priors have different numbers on them, but then we have this one function that converts a log odds to a probability. This inverse logic function. And this is another primitive in PyMC. But the problem with the log odds scale is it's not very intuitive. It's hard to understand what's going on. So we need some additional variables for displaying so that we can look at these variables and understand what's going on. These do not affect the sampling of the model. They basically are only for display. So we have initial mistakes. This is the probability of mistakes on day 0 back in August 2020. We have the probability of mistakes August 2021. That's when I started recording the number of mistakes. And probability of mistakes when I cut the data set last month, October 2023. So again, we'll go over to Jupyter. We'll define the model. We'll sample it. It's a little longer. No error though. And then we'll plot the posterior distributions. So here's the two random variables now. This is in log odd scale. So this is the initial mistakes. It's minus 3.7 with the 94% highest density interval. That's what HDI stands for. Minus 3.9 to minus 3.6. Some uncertainty here. Reduction per day. More uncertainty in the reduction per day. But again, so what does this mean? These are on a log odd scale. Let's look at them in a natural scale. So what this is saying is, in this model, according to this model, if this model is correct, back in 2020, I was making 2.3% mistakes with every note, maybe somewhere between 2 and 2.7. By 2021, I was making 1.5% mistakes, again with some uncertainty. Now, or last month, I'm making 0.64. I'm improving, right? Maybe I'm improving. How do we really know that this model is better? How do we know that it's better? Well, there's PyMC offers a bunch of ways to compare models. We're going to talk about 2 of them tonight. A very cool way is something called posterior predictives. So this is generating fake data from the samples. Take the model, take the samples that came out of the sampling process, run it back through the model, generate fake data. So these fake data is called posterior predictives. And you compare the fake data to the real data. See, do they match? So let's go back to Jupyter. And so this is another sampling process. We're doing it now. We're dropping back to model 0. It's a good thing we had kept model 0 around, but we're dropping back to model 0, and we're using the trace from model 0, the samples, and then comparing it to the real observed data. So how do you read this? The blue are all the fake data that got generated. And the black is the observed data. It's the mistakes I'm actually making. So if we look at the 0 mistakes, the times I made 0 mistakes, the model is predicting I'd make 0 mistakes a lot fewer times than I actually did. A lot fewer times, like half as many. The model is predicting that I'd make 1 mistake fewer times than I'd actually did, but still I'm within the range now. I'm not even within the range. It was 0. For 2, the model is predicting that 2 mistakes. The model is predicting I'm making 2 mistakes more often than what I actually did. So anyway, visually you can see how often the model is predicting this versus how often it actually happened. With these posterior predictives. Okay, so let's do this for model for the new model, the model of improvement. Okay, and I'll go back over here so we can look at them side by side. They don't look a lot different. They look a little different, maybe a little better, but not a lot different. So they're better on some of the out numbers, on some of the 6 mistakes or 7 mistakes. I think 3 mistakes is a little better, 4 mistakes, but they're not a lot better. So that's a little disappointing. Maybe this new model is not really much better than the original no improvement model. There's another way of comparing models. There's many different ways of comparing models here, but another way that I'll talk about tonight is just looking at what's the probability of seeing this data given this model. And these probabilities are very small, so they're expressed as logs, and so it's e to some negative number. So with model 0, the probability of seeing the data that was actually observed is minus 770. With model 2, it's minus 1728, which, by the way, is 1.7 quintillion times more likely. So, much better model.
Still not a good one.
Maybe. I'm not talking about overfitting tonight, by the way. It's a useful topic itself. But okay, let's go to another model. Let's add something to the model that we have. So, high notes are hard to hit. This A here in exercise 147 remember exercise 147 and 138, they're both in the 7th study, they're the same piece of music. It's much harder to hit than this note, this C here, this C that you heard me hit. So I'm glad I didn't play exercise 147. I'm very likely to have missed some of those A's. So we've got to do more data wrangling. We're gonna have another measure, which is the height above C, the number of semitones above C. Semitones, it just means half a note. And so we're going to use this now, the height, for every chance of playing one of these exercises. So this is one new random variable. Now we have this increment height as part of the equation for mistakes sub p. How much more difficult given the height? So everything else is the same, but now we're adding this additional term of difficulty given the height, again in a log-out scale. And the increment sub height is just the increment per semitone plus the number of semitones above C. And so a lot of them, by the way, are 0. They're all below C. So we're going to say, okay, so this is the prior here is maybe nothing, but with one as the standard deviation, another weakly informative prior. So now we have 3 random variables. We have the initial mistakes, we have the reduction every day, and we have the increment per semitone. So this is the same model in PyMC. Oops. I don't think there's anything new here that you haven't seen, but there are another random variable. So let's go over to Jupyter. Oh, here's how you get the probability of the observed data given the models. My notes are hard to hit. We've got a bunch of display deterministics. We're going to sample. Takes a little longer now because there's 3 random variables. And here are the random variables. One thing that's interesting here, even before we kind of look at these in the natural scale, is that a single semitone going from C to C sharp is worth about, what's the division here? About 60 days of practice, something like this. It's quite a bit harder. And there's a fair amount of uncertainty about it. We can plot these things in the natural scale now. Oops, what did I do? Oh, okay, here we are. So this is the initial mistakes, still about the same, maybe a little lower actually, making fewer initial mistakes. Reduction. Did I show this already? No, I'm sorry, I would jump down.
Yeah, right there.
So this is this is plotting the posteriors. Did this before. Okay, well let's just show them. So the initial mistakes are about 1.7% with some uncertainty. By 2021, that's less than 1%. By last month, that's 0.3%. And then with mistakes in the middle register being last month being 0.3%, the high register, the highest one that I play there, it's closer to 1%. So that's interesting. Let's compare the posterior predictives. This looks a lot better actually. Model 3 looks a lot better, much closer. The observed data is much closer to the posterior predictives, to the fake data generated for the model. And the probability, the probability of observed data confirms that. It's a factor of 10 to the 50, the data is a factor of 10 to the 54 more likely in this model. So this was a good jump. This was a good improvement. More sharps or more difficult? I'm going to go faster now for these last 3 models. How am I doing on time? Pretty good. So more sharps are more difficult, so are more flats. It's just nature of a brass instrument that the finger combinations are harder when there's lots of accidentals. Sharps and flats are accidentals. So this one has 0 accidentals. The one I played had 0 accidentals. This one that's just 1 semitone up has 5 accidentals. More data wrangling, number of accidentals. We've got more accidentals, more difficult. The same kind of model now. We've just added an extra term for the increment in accidentals. 4 random variables now. PyMC looks pretty much the same, just addition another random variable. I'll skip going to Jupyter here, and you can see these are the posteriors for the random variables. And an accidental is about, another accidental, another sharp or flat is about half as difficult as another semitone up, which seems intuitively about right. Lots of uncertainty though about the accidentals. Notice how wide that spread is. And here's the posteriors then of in the natural scale. Now we're still making a good improvement actually. No accidentals last month, we get about 0.24% errors. 6 accidentals, we get 0.34% errors. So accidentals certainly have an effect. Posterior predictive looks a little better, particularly on 2. Not a lot better though. And you see the log probability of the data given the model. We're only making a little gain here. 2 more models. Playing an exercise the first time, single exercise, is more difficult than the 100th time. So more data wrangling, or how many prior attempts there were. We'll go right to PyMC here. Prior attempts reduce mistakes. So there's 5 random variables now. How much do prior attempts reduce mistakes? That's another random variable. Posteriors, the reduction per prior attempt is, the mean is about 0.0052. So it's now with this model, prior attempts are much more significant than the reduction per day. 7 times as significant. So.
Yeah, so that's my modeling question. Like, why would you care about per day? Just talk about per session.
Well, I play once every day, so it's.
Okay, if that's consistent.
Yeah, that's consistent. I do occasionally miss a day, like on Valentine's Day, but yeah, once per day. Here they are in the natural scale.
And I guess while we're nitpicking,
Good.
the very high notes are much harder than, like there's an octave or 2 octave range, which should be pretty comfortable for you, right? But then when you go much higher, so you really should not make it linear. You should make it a little bit.
You're
more
right, and in fact, I say that later. I don't have a model for that, but yeah, you're 100% right. So this model is actually a good bit better than Model 4. There's another way to look at these models, which is what's the dependency network of the variables? And I like to draw them out this way, where I have the observed variable in bold. You see the mistakes P. I have the random variables underlined. So we have 5 random variables now. And then the data and the deterministics are in between, joining them all up. So you get a little network diagram, a little dependency diagram of these. Instead of how we've got the height and the accidentals, could do a different model and just have the difficulty for each exercise. 15 different exercises, difficulty for each exercise. And by the way, these are all driven off some common mean and standard deviation across all the exercises. The advantage of that, spoiler alert, is you could then compare that with other studies, not just the 7th study, 6th study, and other things as well, because they would have different means and standard deviations. And then compare in general, how tough is the 7th study compared to how tough the 6th study is. So that's called pooling. It's one of the things that's easy to do in PyMC, hard to do in some other techniques.
So what did you say you do with that diagram?
Sorry, I skipped ahead. This is just the diagram is just for understanding. What I've done here is I've replaced the incremental difficulty due to the height, incremental difficulty due to the accidentals, replace this with the exercise difficulty. So each of the 15 exercises has a different difficulty, which the model figures out basically, and does, by the way, figure out that it's higher and higher is much more difficult. So did that answer your question?
I'm just wondering how do I guess you tease these things out, I guess, for your understanding of the data and so forth.
Oh, how I get to the diagram itself?
Yeah, how do you get to the diagram?
Sorry, I misunderstood. This is literally just taking this PyMC and just figuring out which variables affect which other variables. So for instance, initial mistakes is not affected by anything else. It's a random variable. You see initial mistakes, they're at the top there.
Yeah, it's just that, and it's an interesting way of diagramming out, because you really, it's like a one-to-one mapping almost.
It's a one-to-one mapping.
And
It's a one-to-one
a way
mapping.
that somebody could participate, understanding the data very well, but not knowing the details of PyMC. or
Exactly.
anything particular.
Yeah. So this is saying that the number of mistakes that are made, the is dependent on the probability of making mistakes, and that's dependent on the initial mistakes back in August 2020, the reduction every day due to daily practice, the increment for height, and so on.
So you could come to it the opposite way almost. You could start with this, go the other.
And with clients, I do this.
Yeah.
I start this way because they don't want to see the Python code. Yeah, go ahead.
Yeah, so in the previous slide where you plot the likelihood of like each random variable in the posterior, can we go back to the
Sure. Like
yeah,
this?
yeah, so you've got
These are not the RVs here.
like different for distinct of the 5 random variables.
Sorry, one more time.
Right, so these are the likelihood of random variables in the posterior prediction.
Yes.
So when you plotted the likelihood, so are you like already marginalizing the random variables?
Yeah, except I always have to think about what does marginalizing mean. But yes. The question, by the way, is when these variables are plotted, am I marginalizing over the other random variables? So maybe you can expand on that.
Right, so but in practice we are supposed to take this set of random variables as opposed to
Yes.
maximize the geometry confidence
Yes.
instead of going back to the marginalize this one.
Yes, and in fact, that's exactly what PyMC does. Is it picks values for each of the random variables simultaneously, and then evaluates. The mental model actually still works in this case. So it picks values for each of the 5 from the priors, and says how likely is this data that I'm seeing given this 5. Okay, let's try another 5. Now, 5-dimensional space, that would take forever to actually explore that way, but as a mental model, it's effective.
I thought you could generate those dependency.
I think you can.
Good.
I like to draw them because,
Okay.
I like to draw them because, you can get them very nicely looking. So, and you can do things like have the same except with, different. So now we got 20 variables, 20 random variables, one for each of the exercise, and then one for the mean across all those exercises, one for the standard deviation across all those exercises, reduction daily, reduction per day, and what else? What am I missing? Reduction per prior attempt. So I don't know if this is readable, by the way, but this is now just some of the posteriors for the random variables. Let's go to these are a few of in the natural scale. A lot of uncertainty now about what percentage chance of mistakes, the base percentage chance of mistakes back in 2020, back in 21, or in 23. There's that long tail to the right all of a sudden. Mistakes, the first time something is played is an additional 0.3 mistakes versus the 100th time is 0.02%. Am I reading that right? Is that 0.02%? No, it's 0.2%. So and it's actually not all that significant. Each time something is played, it goes from 0.3% to 0.2%. You'd think you'd get more out of playing something 100 times, but maybe not. The mistakes, but that's for one exercise. That was for exercise 4. For exercise 12, it goes from 1.9% to 1.1%. That one is a lot higher. And then posterior predictives, again, again, we're getting an increase in the probability that this data is explained by the model. So what do we do here? We looked at a lot of models, we added some terms, we got greater complexity, higher fidelity along the way. We could do more with this, I'm not going to, but we could do more. We could do all 28 studies in addition to just the 7th study. Ask if daily improvement is really linear in a log-odd scale, maybe it's not. What about day-to-day variance? It certainly feels when I'm practicing that I'm better on some days than others. Is the improvement from past attempts really linear? If you notice, there were some -1s in there, which are things that were played perfectly the first time. So that could be added to the model as well. So, anyway, it's an introduction. Any further questions? Yeah.
Could you explain more about the difficulty of the exercises, where that measure comes from? Is that something that is provided by the maker of the exercise? Is it like a composite that you created of different variables? Like, how do
The
you go
inherent difficulty of the exercise? Well, the difficulty of the exercise in the the actual exercise, or the difficulty of the exercise in the model?
in the model?
It is learned by the model. So
Okay.
yeah, it's learned by the model.
Okay, but can you explain kind of how it does that? Is it based on kind of the previous additions you made to the model then?
Yeah, I mean, basically what it does is it says there's an inherent difficulty with each of the exercises on a log-odd scale. There's some prior probability of that's based on a mean and a standard deviation that's also learned in the model, and then it does random samplings from this to see what's the best fit to the actual data. And to your point, it's random samplings across the whole joint probability, so it's not just random samplings of this exercise, it's all the exercises and everything else.
Okay.
So yeah, so that's what's
Got it.
that's what's very cool about this, right?
Yeah.
So you could probably take those and make it deterministic like somehow compose them to quantify that as a deterministic,
Yes.
right?
Yes, yeah, quantify the difficulty of a particular exercise. Is that what you're saying?
Yeah.
Yeah. Yeah, it could be done. I probably should have shown that actually. That would have been cool. So.
And then you talked about how it generates the fake data, and then you feed that into another model, maybe halfway through. But why would you do fake data if you have real data?
Because you want to compare the fake data to real data and see how close you are.
But can't you just compare it to the real?
Hold on.
So this is an example. So the blues are the fake data, the posterior predictives.
Right.
And we compare it to the real data to see where we're close, where we're not close. Is this a better model? Is this closer?
But what? It's an analytic function, right? You can just get a mean squared error from the actual
Could do
data,
it.
right?
Could do it. Yeah. Could do it.
Okay.
So.
How does comparing posterior predictives compare to a classical comparison technique?
Geez, I wish I knew. Probably I should know.
It just seems like it's already so complicated that you should make it as simple as possible rather than trying to.
The nice thing about
Well,
posterior
you see where it
predictives, though,
deviates, though.
Where's
Here
Matt
you can
Burns when you
see
need him?
It's not just one, you can see where it is.
you can see where it's different. Exactly. You can see exactly where it's different.
How many dimensions is the model at this point?
20. How many random variables are there? There's 22. 22. Is that right? Let's see. There's 15, 17, 18, 19, 20. 20. So. Yeah.
You try modeling this data using some totally different method just to compare?
No, and the only reason I did this was to do this talk.
I mean, one of the things that's really nice about this method is that you can constrain the model to operate according to your common sense. And I can imagine a lot of clients would insist on getting a work product that sort of is intuitive,
Yeah.
according to their own common sense, that they tell you what it is.
Yeah, you're right. You're right. That's a real advantage of Bayesian methods in general, and PyMC in particular.
I'm I'm just thinking it could be a bit of also a constraint if the model has to like make sense and be interpretable at the end.
Yeah.
What's the difference between HDI and equitable interval?
HDI is the highest density interval. So this is looking at. Let's see if I can remember exactly what this is. This is taking 94% was at 2 standard deviation width, and looking at what's the shortest distance. So the shortest distance that we can get that 94% in. I don't know what the credible interval is. I don't know what.
That was like the corollary to a confidence interval with Bayesian terms.
Yeah.
Like you could make claims about the density, like how much density is in between two values.
Right. Okay.
But it seems like pretty similar.
They're similar. Seem like similar concepts. So. Yeah. Go ahead.
How easy it is to learn, I guess, using PyMC to make these type of models?
I don't think it's that difficult. I think it's I think it's one of these things that you build the model, and it's maybe like getting started is like maybe a 40-hour effort, something like that. It's not that. I mean,
ChatGPT did these things.
yeah. Yeah.
So basically using Monte Carlo over the course of this
Sorry.
exercise about like in which part of this Bayesian model would actually resolve the Monte Carlo.
Yeah. This is the question is which part of the Bayesian model is the Monte Carlo that's part of the name Markov chain Monte Carlo, and that's in the sampling. It's in the sampling that I explicitly said I wasn't going to explain tonight.
So you're saying Monte Carlo comes in when you try to generate big data from the posterior?
No, it's actually even getting to the posterior is Monte Carlo. That's Markov chain Monte Carlo. Those algorithms that I presented earlier, the ones I'm not explaining to Tom, are all Markov chain Monte Carlo.
So do you use the word point the genomics for the base theorem equation?
No, I'm not sure I understand.
Yeah, I'm just trying to figure out in which part of this, like mathematically, why you would use Monte Carlo.
It's actually Markov chain Monte Carlo, so it's not just plain old Monte Carlo.
Yeah. So in which part of the Bayesian modeling process do you need to use the Markov chain Monte Carlo?
Let me show you.
I might make a proposal.
Yeah.
I'm going to propose that this conversation just be a sidebar.
Sounds
and let's head to drinks if you want to grab drinks. And thank you, Dave, for a great presentation. Thank you all for coming. We wish you much future progression towards 0 mistakes.
Okay.
Thank you.
Yeah. Okay. See you next time.
What's the name of the place? People are going.
What's it called? Is it called Courthouse? It's like right across the street. Yeah.
You might want to announce that, just in case
yeah.
people don't know.
Yeah. I assume people will follow. We'll go in a group here momentarily.